cut in the recording. So you now have a fairly complete scientific vocabulary, believe it or not, whether you're going to be a chemist or an aerospace engineer or a forensic scientist or a biomedical engineer or even a physicist. These ideas of energy, motion, force, momentum, variation with time, Newton's laws, conservation laws, these ideas are pretty universal in science. But what I'd like to do is talk a little bit about the philosophy that got us here. Um, the things that we've learned were actually there at the birth of modern science. Modern science emerged through the process of working out what the laws of motion were, as we will see. Um, so I'd like to ask in the beginning, and I'll ask for your answers in chat. Tell me what science is in your experience. Tell me how science is different from other ways of studying our world. And tell me what science looks like when it is being done well and being done in a way so that you can trust the results. Um, I'll be going back over the chat log of this, and people with good comments will get a small amount of extra credit to encourage people's participation. So ponder this for a moment and type your answers into chat. Yes, Griffin. What I mean is to just answer these questions. So tell me in chat what you think science is, how it's different from other ways of studying our world, or maybe what it looks like when it's being done well. Um, so Minheim says science is a method to examine how the world works. Um, there are other methods of examining how the world works. I'm curious how science is different than those other methods. Jacob says trial and error to try and discover. Um, uh, Grace says it's a way to observe the world around us and make conclusions based on observations. So observation is the center of what she has said. Discovering how and why processes work. Lack of bias, that's a huge one. Um, Masson says empirical research. So empiricism is a word we will see again in a moment. Um, the study of how the universe around us functions. Yeah, so this idea of getting at um, the whole universe. We can understand the whole universe at once. We will get that. Shining mentions objectivity, which is the same as lack of bias. Shining, you will see some slides that are familiar from Astro 101. What we're doing here is similar to something we did in Astro 101 last semester that she was in. Um, Again, lack of bias. So objectivity means lack of bias. Calculated and systematic. Samantha talks about mathematical reasoning. Um, Blake goes back to experiment and observation. Garrett's talking about the idea of science as an iterative process, discovering new things we don't know and expanding on things we already know and explaining why. Creating experiments to get answers, according to Julia. Um, Wondering how it all works together. Curiosity being the thing that drives all of this. Um, there's something kind of fundamental that we don't even really talk about. I haven't seen this mentioned much except by students. You don't see it in a lot of the scholarly literature, but you do see it talking to students, which is that the most basic assumption in the scientific method is that we can understand how the world works. If you think that the reason we have lightning is because Zeus has gotten drunk and is having a temper tantrum, then okay, that's a nice story and it's elegant. It's makes for good literature, but that kind of is the end of your progress in understanding thunderstorms. But if you start by saying, hey, we can understand this thing, let's try to figure that out, then you actually have a shot of doing that. So really the most basic thing in the scientific method is the assumption that yes, we are able to wrap our brains around the universe. When Connor says, why does the squirrel only climb that tree? Why do certain clouds show up on certain days? The assumption is we can figure that out. Matthew's talking about cause and effect and understanding why, and the idea of truth in details. Um, Testing and application. Jacob talks about how science uses mathematics as one of its languages, although not its only language. Grace talks about reproducibility. This is a big one. When science is done well, another scientist can prove the exact same thing. So if you do a trial of a new drug to treat some illness, then anybody else ought to be able to do that trial and get the same answer. Taj says that science is study of the physical world rather than human behavior. It turns out that human behavior can be a science as well. So psychology is a perfectly legitimate science. In physics, we're of course interested in the physical world, but there are sciences that govern human behavior as well. Um, Adria is talking about interdisciplinary thinking, that science is different because it combines many different things, for sure. Um, this is why interdisciplinary work is so important. Um, Bryce again loops back to the idea of observation. Dante is talking about the idea that there is a how, not just a what, that we can understand. Um, Dongzhao goes to reproducibility, which is something. Um, Griffin talks about observations. Um, Aiden has a really good point. What makes science different is the fact that the whole system is designed to question its own conclusions. That is huge. That is an enormous safeguard in the scientific method. That scientists are always looking to question their own conclusions to entertain the idea that they might have been wrong. Um, Grace talks again about the primacy of physical evidence. Um, Many people are coming back to that, and Aaron, at the end, the very last chat comment, comes back to our own agency, and I think that is super important. The reason we do this is because um, we can help solve problems. We can help solve problems we have created, and we can help solve problems that make our world better. If you think about the XKCD cartoon in the beginning, right? The whole reason that we are all at home is because the combination of people who study viruses and the combination of people who study epidemics have gotten together and are able to make pretty precise predictions about how this is going to go. And ultimately, the reason we do this is because it makes a better life for everybody. So that's a very good capstone to that conversation, Aaron. So I'm going to scroll back over those at the end of class. Um, we're also going to talk a bit today and more next week about how the scientific process can get derailed. How it is that the safeguards that ensure that scientists don't fool themselves or others fail, and how they are intentionally broken by people who want to fool other people, and how we reach false conclusions. And that's what your paper will be about. I want to take a historical look now through the history of astronomy and natural philosophy and look at how we got here, how it is that we know that F equals ma. And that story is wrapped up with how we know that the sun is at the center of the solar system. And for that story, we have to go back to ancient Greece. 2,500 years ago, there was a civilization that spanned the eastern Mediterranean basin and northern Africa, northeastern Africa in Egypt. And they were very interested in philosophy, they were very interested in the natural world, and they were also very interested in thought and writing things down. And at that time, natural philosophy, as a branch of philosophy in general, was one of the highest pursuits because the Greeks held philosophy in really high esteem. But their idea of doing natural philosophy, so philosophy about the natural world, was asking big fluffy questions like, what is the underlying truth of nature? How is truth beauty? How is beauty truth? They would say things like, for instance, all objects in the night sky must travel in circular paths because circles are perfect and the night sky is perfect and unchanging. Thus, everything in the night sky has got to be based on circles. Kind of seems like weird logic to us, but this was how Greek philosophy worked. Astronomy was a lesser pursuit. It involved answering questions like, how are the stars going to move in the sky? How can I get home at night if I'm navigating by the stars on my boat? Where is Mars going to rise tomorrow and when? And to do astronomy, you had to, of course, actually look at Mars. And that was considered kind of a less noble pursuit than sitting around and eating grapes and talking and arguing. So there was this divide between philosophy and the sort of learning about the world that involved measurement. Much of what we know from that time about astronomy comes from Ptolemy. He was an interesting character. He did most of his work in Egypt, and the name Ptolemy is actually a pharaonic Egyptian name. So this was kind of a multi-continent endeavor here. Um, he took Aristotle's natural philosophy, applied it to the heavens, and came up with a model where the Earth was at the center of everything, and all of the planets moved in complicated patterns up in the sky based on circles that correctly described how they'd move in the night sky. Planetary motion is hard, so these were very complicated patterns, especially if you assume that the Earth is at the center, which is what he did. He made some mistakes. The Muslim astronomers and mathematicians in centuries after that fixed his small errors, but basically this model would let you still predict where the planets would be 1,500 years later. It was remarkably accurate, even though the assumption about where the Earth was, namely that it was at the center of everything, was totally wrong. Now we fast forward to the 1500s. Copernicus, a Danish fellow, proposed instead that the sun, not the Earth, was at the center of the solar system, and the planets went around it in circles. Of course it's circles, right? And there was a little oopsie here in that this explained the rough patterns of the motions of the planets, like the idea that they appear to go forwards and backwards, more simply than Ptolemy could, but the details were actually not as accurate. And Copernicus's publisher put in this really weird note. He wrote, "This is unusual. This work is unusual, but it's just math. We should judge it on whether it makes accurate predictions, whether the math is right, and this is separate from whether it is actually true," with a capital T. Now, this is bonkers to us, right? What you all have said is that in the scientific method, observations and experiments are the prime source of authority. But so we would say, well, if something doesn't make accurate predictions, then it is false. And if something does make accurate predictions, then it might be true. But this note put in by the publisher is kind of evidence that the primacy of experimental data hadn't been established in the 1500s. But then in the next 150 years, two really important things happened. And the big one is this second point. We made some observations of the planets that were more detailed than anything that had ever been done before. This was done by Tycho and his assistants Sophie and Kepler. And Kepler continued working on the problem. He made the measurements, but then he thought hard about them. And he was a Copernican. He thought that the sun was at the center and all of the planets went in circles around it. But he couldn't make that match the data, and he knew how good his data were. He measured them, right? And he saw that no arrangement of circular orbits would fit the data. In particular, Mars was always in the wrong place by at least an eighth of a degree. And he could have said, meh, it's close enough. Who cares about an eighth of a degree? But Kepler made the leap to modern scientific thinking of saying, if something is accurate, if something is the true way the solar system works, it's got to be exactly true. And that there is truth in precise measurement. And then he finally realized that the orbits of planets are ellipses, not circles. And then everything fit. So now we understand how the planets move. Kepler wasn't good at math. I mean, he was pretty good, but not by modern standards. He didn't have calculus. It hadn't been invented yet. He didn't have algebra. It had been invented, but it hadn't soaked into Europe yet. Remember, calculus was invented in the Muslim world. So he couldn't figure out why, but Newton could, because Isaac Newton also developed calculus, fittingly enough, while quarantined from a plague. So Newton was able to take Kepler's realization that the planets moved in ellipses, combine that with some experiments he did on Earth, and realize that F equals ma explains how objects respond to forces, and that this force of gravity explains the elliptical orbits and all motion here on Earth as well. So this is the story of how the modern scientific method emerged. As you all have said, it is different from other sorts of ways of learning about our world because it puts a prime value on experiment and observation, avoiding bias, questioning yourself, and understanding the whole universe all at once. The things that you told me are in fact the same as the bullet points that I have. So I want to kind of briefly look at these kind of in a more philosophical sense. So there are other ways that people have of describing scientific thought and what it is. Here's kind of what I see as the most salient properties of science. The first one is the one you all said, that empiricism, meaning the idea that the prime source of information about our world is measurement. And again, we see this because the new approach, the new learning in the 1500s and 1600s came from people looking at the planets in precise detail, what Tycho, Sophia, and Kepler did, Newton playing with pendulums, and Galileo studying falling objects. Let me get a few questions. So Martin says, if we weren't quarantined, it would be the plague, but it's now just a plague. Lol. Yeah, there's an interesting chart that's gone around about epidemics in human history. The Black Death in the 1300s killed about 300 million people, wiped out 30 to 50% of the population of Western Asia and Europe. That's the biggest one. The second biggest one was smallpox in the New World. The disease introduced by Europeans to a population that had no immunity. So this plague hopefully won't be the plague. Griffin asks, are we going to need to know this for the exam? At the end of this, there is a specific kind of question I will ask you for the exam, and I will tell you what that question is at the end of this unit. Yes, there will be one question about this. The Spanish flu in 1918 was bad, but it was nowhere near as bad as smallpox or the Black Death. But the Spanish flu spread in a similar way to the way that this thing spreads. So the Spanish flu is being used as a good comparison for COVID-19. Of course, now we are much better at epidemiology. Now we are much better at medicine. Um, yeah, I mean, the Spanish flu was bad, and it was so bad that even during World War One, even when lots of people were getting slaughtered on the battlefields of Europe, it made an impact, even in the context of this other huge tragedy that was happening. The Spanish flu also, it was interesting in that it killed a lot of healthy young people, um, including soldiers during the war. So, first big property that we've talked about, primacy of measurement. The second one that someone mentioned is the idea that you have to always question your own conclusions. That if you are wrong, that it is horrible to try to convince someone else of something that is not true. That is one of the worst things that can happen. And so the best person to prove you wrong is yourself. So if you're mistaken about something, you want to be very sure you catch it. Our example here is Kepler. He was convinced that planets went in circles, but he was open to the idea that he might be wrong. And it turns out he convinced himself that he was. The third point is universality, that the laws of physics here are the same as the laws of physics wherever you are, and the same as the laws of physics at another time. And the fourth is objectivity, or the freedom from bias, that we shouldn't allow our particular place or our particular backgrounds to color the way we reason about our world. We see that in this story of the emergence of modern science by we're not putting Earth at the middle before. That was the great mistake of the Greeks, right? They assumed that the Earth was at the center of everything because we are here, so clearly we must be in the most special place in the universe. And then in the 15 and 1600s, we realized that just because we are here doesn't mean we're the middle of everything. So what I want to do now is I want to talk about some guidelines for ensuring that I'll interrupt myself for David's question. Yeah, so, right. This idea here that Earth doesn't get a special place, this is also an example of universality. You're right, it's an example of both. The idea that the laws of physics are the same on Earth and on the moon and in the sun and in distant galaxies. Yeah, that's the same idea. So, the thing that Newton is often credited for his great leap is that the law of gravity for the falling apple on Earth is the same as the law of gravity for the orbiting moon in space. So yeah, it's an example of both. So here are some principles of how to do science well so that we try to make sure that we do not fool ourselves or others. Martin wants me to talk about whether aliens exist. I'm going to be crunched for time. The short answer is I think that extraterrestrial life on the level of bacteria almost certainly exists somewhere else in the universe. It would be a remarkable coincidence for our planet to be the only one, especially because life on Earth emerged so quickly after Earth cooled down. The question of whether intelligent life or even complex multicellular life exists somewhere else in the universe or in our local neighborhood so that we might contact them is a much harder sell. So my personal best guess is bacteria almost certainly, aliens with radio transmitters, got a punt on that one. We can talk more about that later. So here are some broad principles. Based on empiricism, since all of our conclusions are based on data, what that means is that if I have a model about how the universe works, it's only valid within that realm of data that I've checked it against. So Newton did all of his experiments on the law of gravity. GMM over r squared, right? So we know, we have learned here that the force of gravity is gmm over r squared. It turns out this is true regardless of the value of little m. This is this idea of equivalence, the idea that if you write gmm over r squared equals ma, that this mass over on the right-hand side, which represents the mass that responds to forces, is the same m as the m on the left that represents the mass that feels gravity. So on the left, we have, so this m is gravitational mass. This m over here on the right is called inertial mass. And it is not obvious why they should be the same. But we have checked that they are the same, and that's true to 1 part in 10 to the 17th. It's an amazing level of precision, but we had to check that because it turns out when we checked Newton's law of gravity in regions where the force of gravity is very strong, it turns out it's not quite true, and it has to be modified by ideas from relativity. We also need to check Newtonian mechanics for things that are very fast, very large, very small, and it turns out that sometimes F equals ma still works, and sometimes F equals ma needs to be changed a little bit. Doing all of this checking is hard. It helps that we have universality, right? We don't have to throw every rock in the world off of every cliff in the world to understand projectile motion, but we do need to be careful. We need to do big rocks and big cliffs and little cliffs. Maybe we need to take a rock to the moon and see if things are different there. The second principle is skepticism of yourself. And the idea here is that if you make a claim, it is your duty to try to prove yourself wrong and to come up with experiments that might prove yourself wrong and do them. So in 1917, Einstein proposed this new way of thinking about gravity called general relativity that would modify the law of gravity in places where gravity was super strong. It turns out it's, gmm over r squared plus a little bit if gravity is super strong. And Einstein wrote like these 100 pages of really hard math. And then at the end, there's like 3 paragraphs where Einstein says, next time there's a solar eclipse, go look at the stars near the sun. They're going to be in a slightly different place than you think they should be if I am correct. If I am not correct and the stars are in exactly the same place as they were before, then all 100 pages of this math are wrong. But you can go check me next time there's an eclipse and there's one coming up. And this was super powerful, right? It was a huge claim that Einstein made, but it was a very pointed way to prove himself wrong if he was wrong. And of course, we know that, the stars were in fact in the slightly different places that Einstein predicted, and now we know general relativity is correct. The problem is that these ways that you check yourself have to be really diverse, since you've got to check yourself using things you're not familiar with. Einstein wasn't an astronomer, right? He was a mathematician. So this is tough, and this is why scientific collaboration is really important. Another thing, and this is something that many people talked about in chat, is that scientific results need to be reproducible. If you have some claim, you do an experiment, suppose you have some drug that you think cures foot fungus. It's important that other people test that because they ought to get the same result that you do because of universality, and this is a good check to make sure you didn't make a mistake. Finally, the principle of objectivity, which is a freedom from bias, means that diversity in the scientific community is very important because all of us have our own biases based on where we come from, our own personal experiences, and it is important that we have a diverse community of scientists, people of different types, from different backgrounds, um, with different characteristics, in different places, at different times, working on the same problems. Because that sort of diversity means that any misconception that one person may have because of their background has a good chance of being corrected by someone from a different background. So diversity is a source of um, confidence in the scientific community that different people coming from different places um, agree on something. So now I want to shift on to talking about how these things can go wrong. Um, we're going to talk about more examples of that next Thursday when I introduce the topic for the paper. But one example that we're going to talk about now, and the one that will be on your exam, is measurement bias. The idea is that if your data are biased because you had a biased sample, then your answer is also going to be biased. Here's an example from physics. In the 1980s, people thought that some people saw some preliminary evidence that maybe the force of gravity depends on the kind of matter something was. So the idea that F equals big G m over little m, where big G is different for different elements, right? That would be a huge difference, or a huge philosophical difference in how we think of gravity. But in order to verify this, since the effect was small, they built an experiment involving basically going to the top of a tower and measuring something, but they needed very detailed measurements of little g nearby to analyze what they had measured. So they sent people out with some very sensitive, expensive equipment to go make those measurements of little g. And they needed like unbiased measurements of little g in the nearby area. And they had to be super precise. But it had just rained. And low-lying areas were full of water. There were puddles everywhere, like New York right now. So that meant that their measurements of little g were biased toward higher ground. And that bias made them think that the fifth force was real. But once they realized that they were biased against puddles, this went away. So here, nobody meant to like fool anybody. This was an honest mistake made by people who just didn't want to break expensive equipment. But people still, for a while, had an incorrect conclusion. Now imagine that someone was maliciously trying to bullshit someone else. Our world is full of bullshitters, right? Not full of, but there are quite a few. Um, and so it's important to be on guard against people intentionally presenting biased data in order to um, lie to someone else. And this happens all the time. Here's another example, again from XKCD. Um, so we have somebody who thinks jelly beans might cause acne, and she tells the scientists to go investigate. They're playing Minecraft, but eventually she convinces them to go investigate. These two people are cartoon scientists, you know, because this person has safety goggles on and because she has a clipboard. And they go do this, and they find no relationship between jelly beans and acne. This statement, P greater than 0.05 here, all this means is that whatever difference in the amount of acne that people who did and did not eat jelly beans have, there's more than a 5% chance that it's a coincidence. So a standard that's often used is that if there's more than a 5% chance that something is a coincidence, you probably shouldn't get excited about it. Um, so then this guy says, well, that settles it, but maybe there's only some color that causes it. So then they tell the scientists to go get to work again and to hang up their Minecraft game. So now they look at lots of different colors. No link between purple jelly beans, brown jelly beans, pink jelly beans, blue jelly beans, teal jelly beans in all of these experiments that they do. Okay, maybe there's a difference between people who do and don't eat jelly beans and how much acne they have, but there's more than a 5% chance that it's just a fluke. So we can ignore it. Probably not actually a signal. And they do a bunch of other colors too. But when they get to green jelly beans, they see that the probability of the signal they see being a fluke is less than 5%. That means that there's less than a 1 in 20 chance that what they saw was an accident. And the other people go, whoa, right? You found something. You found that green jelly beans are linked to acne. So what happens? Well, the newspapers get all excited. Green jelly beans are linked to acne. There's only a 5% chance this is a coincidence. But what's wrong with this picture? A 5% chance of a coincidence, that's like rolling yeah. um, so 95% confidence, yeah, like that's a little bit different than saying a 5% chance of a coincidence. Um, Lisa, Shinning Lee in the chat, uh, points out that this is cherry picking, that this is a bias in which ones of these experiments I care about. If I have a 20-sided die, I expect 1 in 20 rolls for me to roll a 20, right? Doesn't always work that way in the D&D game, but 1 out of 20 rolls ought to be a 20. But if I ignore all of the rest and only remember the time that I rolled a 20 and got a 1 in 20 coincidence, then that is cherry picking my data, to use the term that Lisa used, the specific term. But this is a kind of reporting bias or sampling bias, right? We have a biased sample of measurements, right? The only one we're thinking about are the green ones. We didn't think about all the other colors of jelly beans. And yeah, as other people are saying, Martin says they tested 20 colors of beans, so one will be a coincidence. David says if you check for lots of them, the probability that one of them will get a false positive is not that low. David, yeah, David said the same thing twice. So, exactly. Bryce makes an interesting point. So, Bryce says that science should be certain, not based on chance. It turns out that whenever you get on an airplane, the best that the people who built that airplane can give you is that there's maybe only 1 in a billion chance that it'll blow up. Or 1 in a trillion, or something like that. It turns out that doing statistics is a very, very powerful tool to draw conclusions. But when you do statistics, you work with probabilities. If you do statistics and get that something is 60% likely, then most of the time what that means is that you need to do more research. And that nobody gets excited about things until a probability is very close to 100% or very close to 0%. The standard used in particle physics, for instance, in like discovering the Higgs boson or discovering a new particle, is roughly that they don't call something a discovery until there's a 1 in a million chance that it's a fluke. It's about 1 in a million. but they still calculate all of those probabilities. So yes, science, we like to be certain, but we always entertain the possibility that we are not uncertain, we are not certain, and we always do our data analysis keeping in mind that we are uncertain and calculating how uncertain we are. So estimating how uncertain you are is basically what statistics is. And it's a profoundly important discipline to get right. This is an example of getting statistics wrong. Um, so the question that's going to be on exam 3 then is one of these. I will present to you a certain story, a story that involves a scientific conclusion being drawn from measurements that may be biased. Um, this is going to be like a short essay question. I want you to write a paragraph. Um, I'm going to ask you basically, tell me if this measurement is biased or not, tell me how if it is, and tell me what effect this bias will cause on our conclusions. Does that clarify for everybody how this material will show up on the exam? It's going to be specifically about diagnosing measurement bias in a brief anecdote that I give you. Yes, I can, Derek. Let me actually share with you the question that I asked. So the question will be, I'm going to present to you a story of a biased measurement or a measurement that might be biased. And I want you to tell me if that measurement is biased, like the story about measuring gravity only on the hills, not in the puddles, or the story about only caring about the green jelly beans. And I want you to tell me if the measurement is biased and what it will do, how it messes up your conclusion. Let me tell you the story that was on the exam last year about this. In World War II, the United States was using bomber aircraft to drop bombs on Nazi Germany. Um, and many of those bomber aircraft came back shot up. They were shot by German anti-aircraft fire. And the US wanted to understand where those aircraft were being shot so they could add more armor to those aircraft. So they got all these aircraft, they came back to base in England, and they had bullet holes in them. So they looked at the airplanes and they said, these airplanes are getting hit all over the place, but they're not getting hit in the engines and they're not getting hit in the cockpit. They're getting hit in the wings, they're getting hit in the tail. Yes, this is survivorship bias, Martin. Exactly. But they're not getting hit in the engines and they're not getting hit in the cockpit. So we should add armor everywhere but the engines and the cockpit. And so, Martin, what's wrong with this story? You've said survivorship bias, but how does that work? Yeah, the only airplanes that they're doing the measurement on are the ones that were shot and survived. If you get shot in the cockpit and the pilot and the controls are damaged, you can't make it home. If you get shot in the engines, too many of them, you can't get it home. So this statistician from Hungary said, wait, no, stop. You're doing exactly the wrong thing. You need to add armor to the engines in the cockpit because this is where, if you get shot here, you cannot survive. So that was an example of survivorship bias. So the question last year was, I told that story and I asked, is the conclusion the Army Air Force has reached about not armoring the engines in the cockpits correct? And yes, the correct answer is what Martin has said, reinforce the areas that do not have bullet holes because the airplanes that got shot there are splattered all over Western Europe. Um, the question will not be that one, but it will be, no, Samantha, you can just explain it. Again, we haven't given the names. Last year when we asked this question, most people figured this out. So it won't be a super hard question. Any other questions about the process of science before we move on to the portion of class that is a review? Okay, what I'd like to do is I'd like to spend about 5 minutes talking through the big ideas, and then spend the rest of class setting up a couple of problems. If you have any questions, please interrupt me in chat right now, and I can always take your questions. So there are two big ideas: conservation of momentum and the work energy theorem and conservation of energy. So conservation of momentum says that if I have objects that are exerting forces only on each other, then their total momentum is constant. And the case that you almost always will encounter where you have objects exerting forces only on each other is a collision or an explosion. Because during a collision or during an explosion, those forces are so huge that all other forces basically don't matter. So the big signal to you that you need to use conservation of momentum is a collision or an explosion. Um, Occasionally you will see a circumstance where there are no external forces. One on the practice exam is when you have a single planet orbiting a single star. So if I've got Jupiter orbiting the sun and there are no other planets nearby, the only force Jupiter feels is from the sun, the only force the sun feels is from Jupiter, so momentum is conserved. Finally, remember momentum is a vector. So if you have a collision or something like this in 2 dimensions, you'll need to write conservation of momentum separately in x and y. We've talked about a couple of different types of collisions. The one that's important for you to recognize is an elastic collision. We will tell you if a problem is describing an elastic collision, but the notable feature of an elastic collision is that kinetic energy is conserved. My finger is messed up. There we go. So if you have a problem with an elastic collision, then I'm just going to point at my notes from 930. That means you're going to have a system of equations because conservation of momentum and conservation of energy both hold. In an inelastic collision, if it's partially inelastic, then some kinetic energy is lost, and if it's fully inelastic, then the objects stick together. And we will always tell you what kind of collision you're looking at. Like, we'll tell you, do these things stick together? We'll tell you if the collision is fully elastic. The work energy theorem is a somewhat more subtle idea. The idea is that the work done by some force can be related to the change in its kinetic energy. Remember, the work done by a force is the dot product of force with displacement. And that dot product can be interpreted in 3 different ways, all of which will give you the same answer. Note that if you've got a force that's in the same direction of motion or a similar direction of motion, that force does positive work. So in this example, so here I've got, suppose these are the force and displacement vectors. So even though these are not exactly in the same direction, this will do positive work here, because notice that one way to write the dot product is force times displacement times the cosine of the angle between them. Cosines of angles that are less than 90 degrees are positive. Oops. But if you've got a situation where the displacement and the force vectors are like this, where they're broadly in opposite directions, then here this angle is greater than 90 degrees, the forces are going in the opposite direction, and this force will slow the object down, does negative work. Finally, forces perpendicular to the direction of motion don't do any work at all. That's like the normal force on a roller coaster sliding down the track, or the tension force in a swinging pendulum. We also talked about potential energy. Potential energy is just another way of keeping track of the work done by conservative forces. So you may either use potential energy to keep track of the work done by gravity and springs, or you can just calculate the work that they do in the normal way. So the work energy theorem without potential energy looks like this. What I'm writing with my pen up top. But if you have forces that you would like to consider as part of potential energy, so gravity and springs, you may also use this formulation of the work energy theorem, where the work term now contains only the work done by non-conservative forces that you're not associating with the potential energy. Forces like friction, there's a question with a person with a rocket pack that I wrote, stuff like that. It's always handy to write these things out in words, what your terms mean. And if you combine potential and kinetic energy together, then you can combine those as mechanical energy, and then this is a statement of conservation of energy. Mechanical energy in the beginning plus other work being done equals mechanical energy in the end. It's not a surprise, right? Conservation of energy is probably the biggest principle in science. Power is just the rate of doing work. It's force dot velocity. You're doing a whole homework set on it, so I probably don't need to review it. That's homework 11. And this is a minor topic on our exam. So we have 7 minutes left. And what I would like to do now is either set up some problems. That's one of the options we can do, is I have a couple of problems where I just outline the problem and we're going to talk about how to do it, or I can answer your questions. So do any of you have questions you'd like me to talk about for the rest of class? Can I show the potential energy slide again? Yes, I can. All of these slides, complete with my doodles, are going to wind up online. Did you have a question about this slide, Samantha? This? This note? Yeah. That one. Can you go over the sample questions? Yes. Samantha, poke me after class and tell me which slides you mean, but I will post these online. So here is a sample question. Good, Samantha. Sorry, I'm just a little crunched for time and I want to make sure everybody gets what they need. So here is a question where we're imagining a train car rolling down a hill. So the hill has got height h. At the top of the hill, there is a train car. At the bottom of the hill, there is a locomotive. So what's going to happen in this problem is the train car slides down to the bottom, collides with the locomotive waiting there, and they're going to go, since the locomotive has its brakes on, they're going to slide a little distance before coming to rest. And what we'd like to do is to find that distance. So what techniques can we use here? So I'll give you all an opportunity. Type in chat what methods I'm going to need to solve this problem. Okay, conservation of energy and conservation of momentum. Lisa says conservation of energy and an inelastic collision. So, and conservation of momentum, as Nathaniel points out, is how we understand an inelastic collision. So, can I use conservation of energy to get from the beginning to the end? Can I do the work energy theorem to go from the first picture to the last picture? No, since I can't calculate the work done in the collision. Yes, Martin has it exactly right. I can only use conservation of energy until the bottom of the hill. So what this means is that I need to draw a second cartoon. I will finish on time today, by the way. I've got enough time to do this problem. So I can only use conservation of energy until right before the collision. So right before the collision, this thing is moving, we'll call it V1, well, V2, because this is the velocity in the second picture. And this one is not moving. So to get from the first picture to the second picture, as Martin says, I can use conservation of energy. So as you all have pointed out, I need to use conservation of momentum to get from the, so we'll label our pictures. We'll label this picture 1, and we'll label this picture 2, and we'll for now label this picture 3. Can I use conservation of momentum to go from picture 2 to picture 3? Isabel says yes. Is momentum conserved here? And in the interest of time, I will just say that it is not. Because in picture 2, I have momentum to the right, and in picture 3, I do not. So what I actually need is another picture right after the collision. And conservation of momentum, that only lets me happen, or only lets me connect what's going on right before the collision to right after the collision. And then finally, I can use conservation of energy again to get from picture 3 to picture 4. And yes, Martin says if the train car rolled 30 feet on the horizontal ground with the friction constant before the collision, you would use energy again. So yes, if there were friction in the first stage of the motion, you'd get that with energy, and momentum would help you relate right before the collision to right after the collision. So I hope that this discussion has helped you unpack, in looking at a problem, what techniques you have to use to understand what part of the motion. Um, I can take questions for maybe 2 more minutes, and then I've got to get set up for the next class. I'm covering someone else's class at 12:30. Um, I will be, so as a reminder for the review hours, I will be in the virtual physics clinic tomorrow from 8 a.m. to 10 a.m. And I will hold some kind of concept review like I did before sometime on Sunday. Matt Rudolph will be in the physics clinic tomorrow from 1 to 3 p.m. If there are any more questions, feel free to type them in chat. Bryce says, if it's not explicitly stated, should we worry about friction or air resistance? Uh, if there, in general, you should not worry about air resistance unless we explicitly tell you. And if there is friction, we will tell you. So during the exam, you may always ask us these questions about what kind of motion is being described and what assumptions you can make. We don't want your exams to be a guessing game. We want them to be you demonstrating your skill. Have a great day, Aiden. And thank you all for your hard work and your attention. Uh, Bye, Jacob. All right, I'm going to stop the recording and hang up Collaborate and get ready for my next class.